first workshop for the coding outreach group. Thank you, Billy, for recording. So this will be our very first in the series. We have, I think it's 8 weeks worth of coding workshops this year. So I'm very excited for everyone to, present their workshops. We've done it a little bit differently this year. So I really appreciate, Matt, for you sending in your idea. And this is all on something that you created and that you wanted to present. Previously, we had designed workshops for people to do and then asked people who we knew had those skills. So I'm really happy that this year people really stepped up and really have some cool ideas that, we've never had before. These are brand new skills for everyone to learn in the department. So I guess, Matt, if you want to take it from there, we can get started.
So yeah, thanks for having me. And I think this one may be a little bit different than some of the others. It'll be a little bit more stat and conceptual focused and less coding, but we do have some fun little miscellaneous coding tasks we're going to get to the second half. But I am going to start with PowerPoint, so let me get that set up. Alrighty, so hopefully everyone sees that. Okay, yep, so today we're going to be talking about GIMME, Group Iterative Multiple Model Estimation. Okay, so GIMME is a modeling technique for network analyses, and we're thinking about networks, we're thinking about time series, and I imagine most of us, if not all of us here, are probably thinking in the fMRI realm. This would also apply to EMA data, or really anything that involves intensive time series. And the idea of GIMME, as we'll get into a little bit more, is that it's really purposed to kind of account for sample heterogeneity. We'll explain what that means, to derive ultimately some more individually precise networks that really reflect the individuals rather than groups, as those can be quite noisy. I learned most of this from a GIMME workshop taught by its creator, Dr. Katie Gates, part of the PIT Summer Methods series. And as in the Markdown document we'll get to eventually, I do have a bunch of links to some of the existing resources. And I do really encourage anyone that ends up using GIMME to really utilize these resources, because GIMME is really well documented both on the R package and Katie Gates's website. So we're going to start with some background on time series networks, heterogeneity, and this thing called ergodicity. I'm going to introduce GIMME and kind of walk through quickly how it works. And then the second half of the workshop, we'll take a break before that, we'll be actually walking through using GIMME in R and some downstream analyses you can do with that. So we'll cover data formatting, running GIMME, some things you can do after that and stuff like that. And I'm going to be just probably only talking about fMRI. But if someone else interested in like EMA or something, just put that in the chat so I can keep that in mind, because I'm presuming most of us here are all thinking fMRI for now. But let me know if not. Okay. So background. So again, we'll be talking about intensive time series data. And when we say intensive, we don't mean 5 time points over like a year. We mean lots of time points. So multiple times a day in EMA or in fMRI, we have those 2-second TRs, right? Or we have a TR of 2, TR of 1. We get X hundred of those in a single scan. That's an intensive time series, our bold signal, let's say, for an ROI. And what a network does is it just defines interrelationships between these variables over time. And we're going to be using terms called nodes and edges. So in fMRI, nodes would be our regions, and each region, like a striatum, would have a time series of bold signal. And edges are just the associations between multiple nodes. So we could have a striatum and POC, 2 nodes, and they would have some sort of edge connecting them. So nodes are just your variables and they have a time series, and edges are just the relationships between 2 different nodes of time series. Within those networks, they can be undirected versus directed. Undirected is probably what most of us are used to. So if we calculate a functional connectivity network, let's say using CON or SPM or FSL, things like that, generally it's undirected, right? It's just a strict correlation value between 2 different nodes. Conversely to that, we can have these things called directed time series networks, which they try to infer some directionality in them. And if we say in the fMRI world, this is when we're thinking about effective connectivity rather than functional connectivity. With the main difference being with effective connectivity, the directional networks, we're hypothesizing an overall model that underlies the observed correlations and kind of test how well this hypothesized model fits the actual data. And if anyone's done work with DCM, dynamic causal modeling, that's effective connectivity. There's numerous ways to think about that. In the GIMME realm, we're going to think about Granger causality, which is really just trying to account for variance explained after accounting for the own node's autocorrelation. That gives us some directionality. And another main difference between these undirected, directed, particularly in the connectivity realm for fMRI, is in functional connectivity, we're considering each set of nodes completely independently. So we correlate X and Y, X and Z, Y and Z, all those are independent. And then this more comprehensive directed network, all of it is interrelated. All the nodes are counting for each other, things like that. I'm going to introduce this word called idiographic. So most of us, when we do networks, we probably end up with an aggregate network where we average across individuals. So we're doing two different groups. We average one functional connectivity network, compare that to a different average functional connectivity network. In contrast to that, we can have idiographic networks where just entirely person specific. So we don't consider anyone else. We just estimate a network for one specific individual. Obviously, that has some pros, and that's 100% precise the individual. But when we do that, we also have some cons that we can't do some of the more typical group comparisons and inferences like that we're used to. And most of us, in most stats, almost all the stats we do are based on means, group averaging. And when we do that, this group averaging, we don't think too hard about it because we just kind of, this is how we're taught from basic stats, intro to stats. And really behind the scenes is kind of this assumption that differences across individuals are quantitative, right? That's just our sampling error or our error. That's the variability. So we get a mean, we get a variance, we just assume that error is okay, attributable to randomness, and we move on. We don't think too much about it. And this is kind of how that looks, right? So we had 4 different individuals. They have this, they all have the same kind of path connectivity setup, but it just differs in the magnitude of the paths, the strength of the correlation. So they're qualitatively similar, but quantitatively differ, and we should attribute that to random error. And that's how I typically think about things. However, this kind of falls apart when we start thinking about heterogeneity. So the heterogeneity problem, as it's been dubbed by some people, is when we average across individuals, we presume that individuals are quantitative. However, and then the group average ends up representing the individuals. However, this doesn't quite hold if differences between individuals are not just random error, but actually qualitative differences. And as I'll point out, if there is substantial qualitative heterogeneity across individuals, the aggregate network ends up representing few, if any, of the individuals. And this is going to be important because if we have a group average network that doesn't really reflect anyone, any of the inferences we make using that group average network don't really end up reflecting the individuals. As a different way of thinking about it, if you average letters A, B, and C, what does that mean, right? You'd get some average letter, but since they differ in kind rather than degree, that average is kind of meaningless. And when you end up using that average model to compare something, it kind of doesn't make any sense. And this, again, to reinforce that, the real difference here is that we're thinking about individuals differ in kind rather than just degree. Supporting that here, we have 4 different networks, 4 different individuals with the networks that look completely different from each other. We get some group average network that considers all of this, but this group average network doesn't really look like any of the individuals. So sure, it is a group average, but it's not really too useful if you go back to thinking about the actual individuals. And this issue is termed ergodicity. So ergodicity is a statistical property where a group level model can be used for individual level inferences. The easiest way to think about it is group to individual generalizability. It has 2 main requirements. Ultimately, they both go to show that intra-individual variation is equal to the inter-individual variation. The first assumption, what we're thinking most about, is homogeneity across individual models, such that they do not differ in kind. The second one that we're not going to think too much about is stationarity over time. And that would be such that the network, if you kind of took different snapshots of the network at different time points, it would look pretty similar. A lot of work has shown that most psychological processes do not meet these criteria for ergodicity, even though we don't think about it too much. And again, a really important limitation is that violations do present valid individual level inferences. And this is a really critical limitation because ultimately, I think for most psychological or neuroscience work, we're thinking about individuals, not groups. But when ergodicity is broken, which it might be in most cases, we can't make valid inferences at the individual level. So in quantitative psych realm, this has been pretty well studied for a while. And Katie Gates, who did a graduate program under Peter Molinar, kind of listened to the field more largely, developed this program called GIMME to try to address these problems. So GIMME, Group Iterative Multiple Model Estimation, its goal is to create person-centered directional connectivity networks by explicitly accounting for inter-individual heterogeneity in kind. So it estimates group level networks that are not group averages, and we'll get to that shortly. And then on top of the group level network, it also estimates individual specific paths that contain both group level information and individual specific data. It's grown a lot, so now there's a lot of different options. You can think about multiple solutions, data-driven subgroups, confirmatory subgroups, and a lot more. GIMME is built on an SCM program called Extended Unified Structural Equation Modeling, and it's entirely data-driven. So here's how a GIMME group level model works, and we can see how it's different from group averaging. So in group averaging, everyone's going to get their own value for each different path, each different edge. We're going to average all those together and see if it's significant or not, essentially. GIMME is different than that because we're not really doing group averages. Instead, we're saying for a given path, let's say from A to B, each person gets one vote. One vote if this path exists or not. When you specify some a priori threshold, the default 75%, and you say that if 75% of the individuals vote, yes, we have this path, then you add it to the group level model saying, okay, this path does actually represent the majority of individuals. So to example here, let's estimate a path for each individual. So all 4 individuals have this path, this up to down, down to up path. So since all 4 have it, it would probably make sense to add it to the group level model. So that's one model estimation process. Then we just iteratively do this over and over and over again until we get our final model. So let's do it one more time. So here we have 3 out of the 4 individuals do have this path. If our threshold is 75%, we would say, okay, that passes our threshold, so we would add that. We could estimate another. Here, only 2 out of the 4 individuals have this path. That's below our threshold, so we wouldn't add it. In real data, you end up getting a lot more paths. It takes a lot longer process, but it's kind of showing the highlight of how GIMME is built on each person gets a vote, and if enough people vote that passes the threshold, then we add this to the group level model under the assumption that the majority of the individuals do have this path, so it actually reflects individuals, which is ultimately the goal.
Matt, can I ask a quick question?
Yeah, please.
So do the groups have to be identified a priori, or can you like use GIMME or like some previous stage to kind of parcelate groups based on like in this case, like functional connectivity patterns? Or like does it have to be like do you have to know the groups ahead of time essentially?
So the question being that could you get subgroups of individuals based on similar connectivity patterns, things like that, without knowing them ahead of time?
Yeah, does GIMME assume that you already know the groups that you're looking at before you run the model?
Let me get like 2 more slides up, and I might answer this question. If not, just ask it again. Okay.
Okay.
I think this might be the next slide. So, so at this point, what we're estimating here is a single group level model for the entire sample. So everyone we have, if it's MDD and control, doesn't matter. Everyone in that sample, unless you want to split them. The next part, which Rana might be getting at, is a subgroup level estimation. So here we finalize a group level model, right? We said these 2 paths are present for the majority of individuals. So we keep these in a group level model. And now we want to try to estimate data-driven subgroups. So these are subgroups that we're not specifying a priori. We have no hypotheses about what they look like. All we're doing is saying, do subgroups of individuals, maybe individuals 1 and 2 and 3 and 4, segregate into more similar connectivity patterns. And it's really kind of the same process. So we'd estimate 2 different paths. Let's say the first and fourth individual have this left to right path. The middle 2 individuals have this down to up path. And then we do this a lot more times in real data. Ultimately, we can use a community detection algorithm to test similarity between individuals and segregate them into 2 different subgroups, right? So now we're estimating data-different subgroups based on individuals that are more similar to each other. Does that answer your question, Rana?
It does, yeah. So, but can I just clarify something? So these subgroup level models are derived from the main group level model still, right? So like whatever applied to the main group has to apply to the subgroups.
Correct, because we said that the group level, whatever threshold, I'm just going to say all, for lack of a better term, all of the individuals do have that group level path. So both subgroups should still have that, but then they are distinct in these subgroup level paths.
Got it. Okay, thank you.
So like one of the cool things about GIMME, as we're kind of pointing out here, is that we get information at multiple different levels. So we get group level information, so all the individuals have this group level paths, then we get subgroup level information. Then once we finalize those subgroups, so you have subgroup A, subgroup B, we actually get individual level information as well. So here are 3 individuals, let's say individuals X and Y, the first 2 are both in subgroup A, so they have the subgroup level paths and the group level paths. Then we can estimate individual specific paths. Right, so all 3 individuals here have the same group level paths. Depending what subgroup in, they have their subgroup level paths. And finally, we estimate the individual specific paths on top of all of those models. So what we're ultimately left with is for each individual, we have a single model that contains shared information for the whole group. if we want subgroups, we can actually turn subgroups off. But if we want subgroups, we would also have shared information for that subgroup. We would have knowledge about which subgroup individuals are forced into. And then finally, we'd have individual specific information, and that allows us to better account for some of this heterogeneity between individuals. And we can do lots of different things with this after the estimation process we'll talk about later. So kind of rewinding this a little bit, just kind of quicker summary. So the first thing we did is we got our time series. So for fMRI data, right, we would get a time series for our different regions of interests. The more regions of interest you have, the more variables you have, the longer GIMME takes, the more complicated it gets. Most of the simulations have been tested with up to about 15 variables. So you get 15 different regions, give or take some. You get the time series from all of them. You would first estimate group level paths. Those group level paths are common to everyone. You then, if you wanted to find subgroups, you could cluster individuals into data-driven post hoc subgroups, so completely exploratory, no hypotheses. You'd get subgroup-specific paths, and then for each individual, you end with a single path for them. And let's see if we want to talk about this. So behind the scenes, how this is working, it's all based on structural equation modeling. So when we say like each individual gets a vote if that path exists or not, that's using what's called modification indices. And modification indices are essentially questions of, would the model fit for a single individual improve if we freed a certain path? So if we add a path on for a certain individual, we estimate this relationship, would the model fit for that individual improve? So what GIMME is really testing is, if we have a path, let's say from X to Y, would that improve significantly the model fit for at least 75% of individuals? If so, what's added on? That's at the group level. And then finally, at the individual level, we're only thinking about that single person. Would this improve the model fit for the single person? If so, cool, let's add it on. And I think that's kind of the main thing to know, that modification indices. And then once you go through the whole process, the final model is actually estimated from, so you have all these different paths that we estimated through these different iterations. And the final thing of it is we estimate a confirmatory model specifying the paths which identified in an exploratory way. And that just gives us some clean coefficients for each path we identified. So we ultimately end with a specific network for each individual. Okay. Let's take a pause there for any questions on the conceptual background for GIMME, why we're doing it, how it's working, different stages of it.
And so you're saying it can give directionality between the regions of interest, or is it just like these are related?
Yep. It will only give directionality. So all of GIMME networks will be directional. And there's been a recent paper about that. So the directionality is difficult, especially in fMRI, because things can be so noisy. And one of the things GIMME is built on, you can see here, if you look over here, we have these autoregressive paths, because I mentioned that the directionality is based on range causality, which is considering the autocorrelation between each variable. In fMRI data, this autocorrelation can be very strong, especially as your TR shrink. So if like a lot of resting state data, your TR will be very small. You're getting lots of different scans very quickly, and that makes the autocorrelation very strong. And there's just like a lot of more complicated work of like the strength of that autocorrelation ends up affecting your ability to detect directionality quite a bit. A little more complicated than we'll get into today, but something to think about. Yeah,
Matt, just based on what you were just talking about with the shorter TRs, the autocorrelation will end up mucking up a bunch of things. But have folks relied only on like scan T to scan T+1 with short TRs, or have they looked at longer lags also?
Can you rephrase that question?
So the challenge with the autocorrelation with the short TRs is that you have such strong time T to time T+1 associations. Right. But some of the directional effects from one region to a different region might play out over a longer lag. So it could be a lag 2, a lag 3, a lag 4. Have any of the GIMME folks played with that in addition to just the lag 1?
I don't think so. And that's actually something I should have mentioned here. So probably all we were thinking about as I was talking through things are contemporaneous relationships, meaning occurring at the same time. But one thing Tom is pointing out here is GIMME can also estimate lagged relationships, meaning the effect of node X influences node Y, like 1 second later, 1 TR later, one time point later. And I think to Tom's question, GIMME is working on a lag of 1. So 1 time point. And I think that's all that's been tested to this point. I don't think people have tested longer lag times than that. Is that what you're asking, Tom?
Yep, that's exactly it.
Probably something that should be looked at. And so, for example, like we're talking about this like autoaggressive issue for like really short TRs, really short time points between really short intervals between observations. Like I'm aware of some people that have run into issues, for example, using GIMME with like ABCD fMRI data where the TR is like 0.7 seconds. And I think they're just finding essentially no group level paths besides autocorrelations, because if you think about it, again, these paths are the variance explained after accounting for the autocorrelation. So if this autocorrelation is incredibly strong, meaning the measurement at T is like really close to the measure at T plus 1, you're gonna have almost no variation left over that can be explained by any of the variables. So people are thinking about ways to like downsample the TR and things like that. Cool. Other questions before moving on to the R aspect of things? Stop share for a second while I get my R set up. So for those of you playing along, within the workshop notes, there should be a link to download some raw data. So that would be good if people could do, but actually, and I think probably better to do, if you're going to run GIMME, I'll do that after the workshop, or you can start it now, maybe get a second window of R open if you really want to, just because it'll probably take a couple of hours to run. And we won't do that today, but I also uploaded the output of the GIMME estimation process. That would definitely be good to get. And I think that's also somewhere on the GitHub. Maybe Katie can relay that info as I'm getting this up.
Yeah, I have the link in the chat. You actually might have to go to the main page and download the whole coding outreach group because of the way GitHub is, which is kind of annoying. But if you download the entire COG summer workshops as a zip file, you can unload that and it'll automatically download all the data for you. So if anyone has issues with that in particular with GitHub, let us know. There's also like a little mini tutorial that is on the main page of the coding outreach group, the summer workshop series for this year as well. So.
And just so everyone's following, what I'm going to mostly talk about as we get a little bit further is we're going to need this file, this GIMME output RDS. RDS essentially just an R object. It can be any sort of type of object. We'll see shortly it's a list file, but we're going to need this and loading that into R. You can load it in by just doing read RDS capitalized. It'll be this file. Okay. So let me move to R. Okay, and I have this whole document. Actually, we probably should do that instead. So sorry, I'm getting confused. Okay, so the workshop itself has been knitted onto an HTML file you can find on the GitHub. And I'm going to be going back and forth between that and the actual R just so we can like play around with our coding. Okay, so all of this, like I made it such that you can just read it and like use that as a resource afterwards. I'm not going to be reading it to you here. The GIMME is very easy to install and use. It's just a R package on CRAN, so that's been good. There's a lot of documentation making it easy with R. It's just install packages, GIMME in quotation marks. We don't have to remove that comment. And then to load the library, you only have to do this one time on your computer. Then to load the library, whenever you open R, you would need to do library GIMME. Okay, so the first part of GIMME is we need to make sure that our data is formatted into a way that GIMME can read it. There are two ways of doing that. GIMME can read R list objects, where each element of the list is a separate individual's file. Or what I found more convenient is a CSV format such that you have a folder where each folder only consisting of CSV files, where each CSV file is one individual's data set. So what that ends up looking like here is this to be one individual data set. So let's say this is subject 001. Then we have our columns. Our columns are the variables, our nodes. So we have caudate, putamen, they can be named. I think you should name them. So these are all of our fMRI regions of interests. GIMME can also estimate task events. So here we have a reward anticipation time, a reward outcome time. And these are all coded 0, 1. So all the zeros, which should be most of the times here, saying this event is not happening. And for these two TRs, we're saying these at this 2 time points, the reward anticipation phase is happening, right? So here we're getting reward anticipation, here we're getting reward outcome, and so on. We would have one of these files for each individual. So all individuals will have the exact same columns. They have the exact same variables, I should say, but the data will differ. They also can differ in the length, so the rows can differ, and they can also have missing data. GIMME doesn't care about the length or missing data or any of that. All of that doesn't end up mattering too much, unless you have a massive amount, I should say. But what does need to stay the same is the columns and the headers between the columns. If you're working with fMRI data, which I kind of think most of us are, when you extract time series from different regions of interest, most programs give the data in a format like this. So generally, we extract fMRI time series data. It's not too much work to get these CSVs. If anyone's working with more like EMA style data or other types of data, you might get some more like long format data where it's not separate files per individual, but a single data set that has all the individuals in the same data set, kind of like a long format. And as one of our, let's get this up. And it's one of our first first tasks. I want to think about how if we have a long formatted data set, let's say it's called long DF. If anyone knows a quick couple R commands that we can use to split a long formatted data set based on ID into individual data frames for each participant, and then save each of those into an individual CSV file. Right. So we have a long format data set, which I should have put a picture of it, but we'll have something like there's an ID column, a time point column, and then our variables, right? And we want to split this up such that each individual has its own complete distinct data set. I'll give a couple minutes to think about that, or if anyone has some ideas of starting points, we could also toss those out.
Holly, you look like you have an idea. You're talking to yourself.
Shut up, Katie. No, I mean, I would write a loop, but I'd have to pull up some old code. Do that.
So a loop could be one way to do it. I found a convenient function that does this actually really quickly. I think just in general, it's pretty helpful for this long format kind of thing. So let's say we have this data frame called long DF. We can just use the split function. This is base R, not tidyverse, just base R. And we'll split it. So we'll get essentially splitting this long data frame based on whatever variable we'll tell it to, but split it by the ID. So now we have a data list, and each element is a data frame base that was split by their ID. Let's see if this is what Billy said. And Billy said loops for everything. Yeah, me too. But Tom gets mad at me, so I'm trying not to use loops too much. So then once we have this data list, again, where each element in the list is someone's own data frame, we can then create a vector of file names. So here I'm pasting some directory of interest, right? So let's say this is just C/desktop/GIMME workshop, something like that. So that'd be the prefix for every file name. Then we have the names of the data list. Since we split it by the ID, that would just be the actual ID of each participant. So probably 001, 002, 003. And then we'd have .csv. So ultimately, this would create a bunch of different vectors that are essentially path participant CSV. So it looks something like, I'll put it in the chat. It end up looking something like that, give or take, right? And then we can use this map function, which is really cool. So what map is doing is it's applying a function, right, CSV, over respective list. and these just work iteratively like the same. So data list 001 would apply to file names 001. So essentially doing write CSV, the input is data list. The first element of that would be participant one's data. The first element of file names would be the name for participant one. So it's essentially writing the data for the first participant using that first element of the list. And this would ultimately populate a folder in your home directory with each individual's data set. So just 3 lines of code. We're going from a long data frame to a full directory of data. Okay, so the next step should be easier for us to think about. We're going to think about some GIMME arguments. So once you've loaded GIMME, it's pretty easy to use. The function is just GIMME SCM. Here, there's a bunch of different arguments. So if you have GIMME pulled up in R, you could just do help GIMME. You could see all the different arguments. There's a lot going on. I just pasted the main ones here. To quickly walk through them, we have to specify where our data is. So if you've stored your data into an R list, you would just point it to that list. If you stored it in a directory, you would paste a string with the quotations to that directory in your computer. Your output directory. So this would be, you can just specify some place in your computer to store the output. You don't need to make this folder. GIMME will do it for you. Separation. So if you're doing a CSV files, that's comma separated. So this would be a comma. Header, true or false. So does your file have headers in it, or should GIMME make them for you? Autoregressive, true or false. I think for as far as GIMME is concerned, you should probably always want this true. Do we want plots? Yes. So do we want, so the subgroup function is data-driven subgroups. Do we want to estimate those? I think one of the cool things about GIMME is these data-driven subgroups. So I think let's play around with it with on true. You could also make it false. There also is confirmatory subgroups, which we'll talk about in a little bit later. So exogenous variables are not time series, or it's not the exogenous variables means they can predict other variables but can't be predicted, right? So if you were doing EMA, this would be like weather, right? Like weather can predict momentary emotion, but our momentary emotion can't predict weather. It's probably not. In fMRI, this would probably be task events, right? The task events should be able to predict our bold response, but our bold response should probably not be predicting the task event. In fMRI, we know the hemodynamic response function. So if we have any exogenous variables like task events, we should convolve those with the hemodynamic response function. So any exogenous variables should probably be repeated right here because we need to convolve them.
Oh, I have a question.
Go ahead.
So your exogenous variables here are outcome and anticipation, right?
Yep.
And so you would put the header names?
Yes, exactly. I'd put, I'm not going to tell you what I'll put. I'm going to have you guys do this in a second yourselves. But yes, correct. It'd be something like the header names.
Okay, cool. Thanks.
You would then, you'd say put those here. You would say you'd probably want those convolved. You need to specify what length you want them convolved by. We'll see if anyone remembers that in a second. That's the length of it. We should probably standardize our results, just makes things quickly. So the default group cutoff is 0.75. That's 75% of individuals need a certain value. So you could also change that if you wanted to. Generally, most people should keep it at 75. You could also make it the cutoff for subgroups. So for individuals within the same subgroups, what percentage of pass do they need to share to be that? That could be, I think people generally have this lower than the group cutoff just because subgroups are noisy and smaller, but really can be whatever you want. In multiple solutions, MS allow, what multiple solutions do is with SCM, particularly with this directionality stuff, you can run into situations where you could kind of get two statistically equivalent models, meaning two different models can give you the same model fit, and GIMME or really any other SCM approach doesn't really have a good way of saying which model is better. So what MS would do, multiple solution would do, if you made this true, it would dramatically increase the estimation time. But for every branching point where GIMME could estimate a model or two different models that are statistically fit equivalent, it would keep both. And then it would keep branching it off over and over and over again. So ultimately you could end up with a lot of different models. And then you get to look at the end outcomes for each of them and end up using more like theoretical information to see which one you want to keep. This is particularly good for some of the directionality stuff, but just keeping it false for now just because of the time constraints it has on. So what I would like you all to do quickly is to copy paste this block of code into your own R program and fill in each of these arguments. It shouldn't be too tricky, but just kind of taking a second to think about if we're understanding what these arguments are asking for within GIMME. You can use the comments I have here for help, or also that GIMME help command gives them more information on the arguments. And we're going to be thinking about that example data I've uploaded onto the GitHub. So using that example data, how would we fill these out? I'll give you guys a couple minutes to do that.
If anyone has trouble loading anything, let me know. It's funny because I did this the other day and I was able to get the package to work, but right now it's giving me some trouble. I don't know what I did.
Yeah, any trouble, just speak up. We'll see what we can work through. Again, the data should be on the GitHub, and then you're just copying this block of code and adding in the arguments you think should go here. Yep, our documentation is definitely helpful for this. Those playing along, how far are we? Thirty more seconds, so we'll start thinking about it.
Is everyone able to get everything to load? Is there like a certain point where we're getting stuck? Done these coding outreach group workshops too long, I will force people to participate in the coding.
Yeah,
I'm not
it's,
gonna lie,
I was,
I'm not. Oh, go ahead, Billy.
no, go ahead. I was gonna say gibberish. Go ahead.
I was just gonna say, I'm not like really trying to run this right now, but I am just kind of like putting in skeleton code and filling the thing to try to understand stuff.
No, yeah, I would definitely recommend pausing on running it, but seeing the skeleton code would be good. Okay, so if you're following along also on the HTML document, you can click this code button right here to see me fill it out for you. But let's walk through it. Okay, so for the data, again, we're just pasting a directory of the data. I'm not sure why this weird code here, but it would just kind of be like C like here you'd probably like C/desktop/GIMME workshop /example code, that directory. And with that, we're using CSV files, so our separation is a comma. We do have headers in the file, right? So those are our column names. We do have those. Our output is wherever directory we want. I see why I have this directory here. So somewhere earlier.
Yeah, sorry. That was when I was fixing it, I cleaned that up. Sorry about that.
Yeah, so earlier I specified a directory. So you would specify this to be whatever on your computer you want to do this GIMME stuff in. So this would be users/Billy/GIMME kind of thing. So this would be pasting that earlier string with data at the end. So we'd have /data. So that'd be a good place to have our data. Here would be having that earlier string /output. That's where we'd be storing the output. again, I think autoaggressive and plots should always just be true for GIMME. No reason not to that I'm aware of. Subgroups, why not? Let's estimate some data to different subgroups. Standardizing should be true. Okay, so Holly, this is what you were asking earlier. So here are our task event data. So we have two exogenous variables, our outcome variable, our anticipation variable. We need to convolve these with the HRF. So we'll have the same two variables being convolved. If anyone remembered our standard hemodynamic response function of 16 seconds, that's what goes here, the length of the involved HRF. Column interval, this is maybe a little bit tougher to look at because I didn't tell you it earlier, but if you use the help GIMME command, it pretty much just tells you straight up that this is the TR, which for this study was 2. I just didn't tell you that. Then we have a group cutoff and our sub cutoff. These are just the two defaults I have here. You can change these to whatever you want to be. For fMRI, I think subgroup cutoff a bit lower can make some sense, but if you have like a really strong predictions of what subgroups should look like, maybe you'd want to increase this, or if you think things are noisy and weird, maybe keep it lower. Or you could change this from different models and see kind of how things are robust or not, right? And that's all it is for running GIMME. Yep, Holly?
Matt, sorry, convolve length. I missed your explanation of that.
So all this is the length of the function we're convolving our two task events by. And this 16 seconds is just the standardized hemodynamic response function length. It's just 16 seconds. So for most fMRI data, we're going to be using 16 here.
Okay, thanks.
Let's see what the what GIMME says about that. Right, so if you look at help GIMME, the description for the conv length argument is expected response length in seconds for functional MRI bold. This defaults to 16 seconds as the default for the hemodynamic response function. I think one of the future areas of growth for GIMME is that other modeling approaches like DCM can be a little bit more flexible in some of these HRF, whereas GIMME, you're just kind of putting in the 16-second default for all regions. But I think more and more work is showing that the HRF actually differs based on where in the brain you're looking. So probably an area for future growth. Yeah, but at this point, we would have all the GIMME arguments filled in. We would just run this command. I don't recommend doing that right now because this will take a few hours. What I did for you is I saved this. I saved the output object, GIMME output.rds, which I named this to right here. Then I uploaded that to the GitHub. So this is the object you need to get to move forward with the workshop. And once you've downloaded it, all you need to do to get into R is just read RDS. That. So I would run this exact line so we have all the names consistent, so we didn't really change any of that. So hopefully everyone can move forward with that. Has everyone been able to get this GIMME output object read in? 1 second, sure.
I'm able to read it in, but it's not plotting it.
Did you run that?
Yeah. It's also like I did this before, so I don't know. Like I went through the whole workshop before, so I'm not sure why it's. I don't know if anyone else is having. Maybe it's just because it's loaded before. My R is like, "What are you doing? You did this yesterday."
It's plotting for me. Are you getting a specific error message?
Yeah, but the XY coordinates. It also might be. I think my packages are messed up for some reason.
My guess is probably an order of packages that you read in.
Yeah.
That's like something with R that like sometimes tricks me up. But like if you load one package for another, then things get weird.
Yeah.
Would it be easy if you like reset your R really quickly, like restart the session?
Yeah.
And just load GIMME?
I'll try that.
Ollie, how are you doing? Have you gotten this part done?
Yeah, I'm a little behind, but I'm fine. Something's just taking a minute to.
No problem.
But thank you.
I also do know if you've recently updated your, I don't remember if it's R or R Studio, but there's like some bug that they're having where it's just like generating a ton of like errors that haven't been patched yet. I just saw that yesterday. I don't know if that's relevant, Katie, but
I think that is what happens. Yeah, no, I did recently. I think this morning I updated it because it kept doing it. I was like, oh, I'll update it before. No, bad idea.
Yeah, it keeps randomly throwing me like a parse key error or something like that. And I was reading on the GitHub for it, and people were saying it's like a common thing that just hasn't been fixed yet. But anyway.
We love it.
I've clicked ignore update like 100 times and it keeps coming up. I'm like, I don't want to. I know
I
you're
know
gonna break
this
something,
version
but
works. It's like this version works. I don't want to touch it anymore.
I try to find a point where I'm like finished all my projects like that. I can safely update so things don't change. But yeah. Okay. What's and just another reminder, like I have all of this stuff I'm describing written out in this workshop, and my writing may or may not be clearer than my talking as well. So you can always go back to that. But for now, if we just hopefully if things work right, if you load this data in and just plot the entire, this is a list object in R. If you just plot it, you get something like this. So let me actually just share my whole screen so we can try to do this. So hopefully you all just see my R now. Right, so the only thing I've loaded in is this GIMME out object. I've loaded in GIMME, library GIMME. So if I just do, hopefully this works. Right, and I'd get some plot like this. And this is the same thing I uploaded here. And let's take a second to look at this. Okay, so because this is probably kind of the things you're presenting in manuscripts if you use GIMME. So we have the first thing to look at are all these black bold paths. Potentially even before that, we have these autoregressive paths for each ROI. So they are present for all 15, and this is telling us that all 15 ROIs did have significant autocorrelations, which for fMRI, I think you're probably going to get that for every variable you use. After those, we have these black paths. These are our group level paths, right? So that means all of these black bolded paths are present for at least 75% of the individuals. 75% of the individuals voted yes, this path would improve my model fit. And then since at least 75% voted yes, we even estimate them for also the 25% or fewer, we don't know, that did not. So these are present for everyone. Moving to the green paths, the green paths are subgroup specific paths. So these are subgroup level paths. From this plot, we can't really see which paths belong to which subgroups. We just know that the green paths belong to one subgroup or another. But we can better look at that later. And then behind the scenes, we have all of these little faint gray paths, and some are dashed and some are continuous. These fainter gray paths are all the individual specific paths. So that means at least one individual, could be more, in a path from the anticipation task affecting the ACC. And this path was not present in the group or subgroup level, right? And we can see there are a lot of these paths, and just again highlighting that there's a pretty good heterogeneity in the amount of paths that be present between individuals, right? Because there's a lot of individual specific paths that are not bolded group level paths. The continuous paths are contemporaneous relationships, meaning X affects Y at the same time. The lagged paths are lagged relationships, meaning X affects Y at a later time point. A lag of one TR. All of that clear for understanding this plot? This is kind of...
Can you repeat what you said about the dashed lines and lag, please?
Right. So the dashed lines, which looks like only the individual, we don't see any lagged group level paths, but so the lagged lines that are individual specific, these are dashed are lagged relationships. So that means, looks like we have one from the ROFC, the right orbitofrontal cortex, pointing to the right caudate. So that means the right orbitofrontal cortex at T, so let's say at the halfway point of the scan, is affecting the time series of the right caudate one TR after that. So this is TR like 10 seconds in, it would be affecting the caudate at 12 seconds in, essentially. It's a lag relationship.
Got it. Okay, thank you.
And this path, it could be, we'd have to check, it could be positive or negative. So it could be, if it was positive, we're saying if the increase in OFC would predict an increase in this one TR later, whereas negative, the ROFC would predict a decrease in this 1 second later. And again, the directionality here does matter, and if we look close enough, we can see the arrowheads showing us the directions. Okay.
What distinguishes a positive versus a negative association?
So in these paths, I don't think it's in these plots, I don't think it's shown, but we'll look in the output object itself pretty soon. We can see some more concrete information. That's important to see. Good question. Okay. Before we move forward, besides those questions, are we good with these plots, understanding them? These are pretty core to GIMME. Yeah.
One more question. The
Sure.
plots are clear. How do you know how much the lag is? Is that the lag, like the hemodynamic response function lag time?
So the lag is just a one interval. So for fMRI, the interval is the TR, so it'd be 2 seconds. For EMA, the interval could be from like morning to afternoon, things like that. It's a lag of 1 T.
Okay. And it's always just 1.
Let me just double check this while we're running the point.
Yeah, Matt, the way that the lagging happens, it's just a single lag from one observation to the next. I don't think that there's a way of altering that unless you go into the source code to put it at a lag 2 or any other lag.
So you check this. I don't need to find this somewhere.
It's based in the way that so you only give it the data input is just the raw time series. Under the hood, it creates a single lag. It creates lag variables for all of them that are just the single lag.
Okay, single lag. Yep. Okay, next on.
Okay, so then if there were, say, a lagged relationship that was like more than 1 TR in length, this model wouldn't capture that. Okay. Thank you.
Okay. So this is kind of just like the first thing we look at when we run GIMME. We just get a plot and we can see a group level pass, a group level pass, blah, blah, blah. See there's a good amount of individual level pass, so a good amount of heterogeneity. But to get more concrete information, you want to look at the output objects. So I don't think you all won't, unless you run it yourselves and wait a couple hours, you'll eventually get this output directory. You won't have this yet, but to kind of tell you what this looks like, we'd have these 2 folders, individual subgroup, and we'd have all these different files. And all the same information that's captured in the directory is also captured in the R object that I have uploaded for you all to download. So you are not missing any information, just the way it's organized. But to look at things in the directory, what it would look like, the most important information is going to be in this individual estimates.csv file. And I'll show you where this is in the R object shortly. So just this file, and it looks like this. It's just a long formatted data frame. So we'd have each row is a path. So subject 1, path from the caudate to the lagged caudate. So it's an autoregressive path. We have a beta coefficient, standard error, a z-value, a p-value. It's a group level path. And here we get to see what subgroup this individual is in. So in this screenshot, all of these rows are subgroup 1 or subject 1. So we have at least 37 rows for subject 1, likely more. And eventually, once we've captured all of subject 1's paths, the next rows will be all of subject 2, and so on. And GIMME is formatted in a nice way such that the autoregressive paths are always first. So you can see the first 15 paths, we had 15 RYs. The first 15 paths are all autoregressive, caudate to caudate lag, left caudate lag, right putamen lag, right? And then move down into the different group level paths. We have a group level path from the right to left caudate. Okay. And eventually, once we run out of group level paths, we get to these individual level paths. So that means this path from the posterior cingulate cortex to the left nucleus accumbens was not present in the group, but it was present for subject 1. And that's when we start seeing more unique information, right? And here we're also seeing the direction in the with paths are positive or negative, right? So we have negative autocorrelations, positive autocorrelations, positive effects, things like that. Okay. And we'll look at this again in the R object pretty soon. So I showed you earlier there was a subgroup level directory. If we click into that, here we get the subgroup specific paths. So we had 2 subgroups from GIMME. It could have estimated any number of them. Since we only gave it 20 individuals, there's probably not really any true subgroups, but it gave us 2. And here we have subgroup 1. Here we have subgroup 2. Immediately you can see that subgroup 2 is much more dense, right? So this gets into more like network science theory, things like that. But overall, you suggest that individuals in subgroup 2 have much more dense interconnected networks, right? Whereas subgroup 1 is much more sparse. We have some cortical relationships, looks like here, and from the caudate to the PCC, things like that. Subgroup 2, we've got a lot going on. If you walk through this markdown file yourself, a couple different points, I link some cool tutorials and how you can run some additional sensitivity analyses to see how valid or not the subgroups are. I'm not going to get into that, but at some point I link pretty cool things from that. Yeah, right here is a cool program you could use. Okay, but for what you all actually have is this gimme out object. So let's just go into my R so I can prove it actually looks like this and exists. And here's what it looks like. We have all these different, so it's a list object, we have lists within lists, and a whole different bunch of information. What I was showing you earlier, that CSV file with all the path information, that info is all captured here in path SE best. So if you run, cool thing about R, if you like get to the aspect of the list you want, go over here, click this, you can get the code to get that object, right? So if you run that, here's all the same information, right? In the same way, we have subject, left-hand side of the path, right-hand side of the path, beta, SE, blah, 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 right? This is the exact same information we already showed. And you can see here, now we can see subject 2 data. We also see subgroup level paths, right? This is for subject 1. Right here, we start seeing subject 2's data. So we can see this is in a long format data frame, right? So this path SE best element of the list has all the important information in it, forget me, essentially. And we'll play with this a little bit more in some of the coding tasks toward the end. Just so everyone's on the same page, LHS, RHS, that's left-hand side and right-hand side. This is thinking essentially like a SEM model. So the left-hand side, if we're like writing this in Lavon, for example, we'd have like left-hand side being regressed on right-hand side, right? Plus like a covariate. It would kind of look like that. So that's kind of the equation we would write. That's like what the LHS and RHS mean. What that ends up meaning. Yeah, sorry.
I didn't, what do you mean by that? I'm sorry. Is it
Yeah, sure.
brain hemispheres? No.
Nope. So within GIMME, we have these LHS variables and RHS variables. And if we look, like when we look at this file, so we have like the left-hand side, it's the right caudate being regressed on the right caudate lag. So LHS stands for left hand, RHS stands for right hand. And where that comes from is like if you're writing like an SEM equation like this. It's like if you were writing in Lavon syntax, factor 1 being regressed on other things, you would write it like this. So for example,
Matt, just one other way. The
Yep.
dependent variable is always regressed on the independent variable, so it's just that kind of statistical grammar that it's imposing.
So like these two things are equivalent. So the left-hand side is your dependent variable. And if we're back at the plots, the arrow is going to be pointing toward the dependent variable. So the arrow is going to be pointing toward the left-hand side column. Toward the right caudate in this example. That cleared up, Holly?
Yeah, thanks. Yeah.
Yep. Ready. And let's see, there's like somewhere in these. So we also in the GIMME object have all of the data that was inputted. So here are 20 subjects. The 32 rows. So if you remember, we inputted 17 rows, 15 were columns, or 15 were the variables, 2 were task events. So we had 17. 32 comes from because we had 15 variables. Like Tom was mentioning, GIMME also creates the lagged form of those variables, right? So we had right caudate lag. So for those 15 variables, we need to double all of them because each one gets a lag. So that gives us 30, and then the 2 extra task events, right? So we have 15 times 2 plus 2. So that's the data GIMME used to run everything. And the other probably relevant sublist is this fit object, where you have all your different SEM fit indices. So you chi-squareds, RMSEAs, CFIs, BIC, AIC, things like that. generally reported, like any papers I see using GIMME, they generally report kind of like average of these fit indices to see how well the model fits or not. Since I just gave like 20 random individuals, I'm not bothering looking at it because it's probably not the best fit, but it's okay. All right, so I guess I put a little checkpoint in here. So this far, we've loaded our data into R, we've learned some of the GIMME arguments, and we've just started to explore some of the output variables. In general, I think the key thing to get from GIMME is the different levels of information we have. So we have group level paths that are present for everyone, but though the paths are present for everyone, their magnitudes can differ. So all of the individuals will have this right OFC, right insula path, but the beta will differ between individuals, as will the SE, blah, 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 right? So you can test differences. So like I know all individuals have this path, but how do differences in its weight relate to external outcomes, for example? You can do tests like that. For the individual level paths, so let's say only subject 1 has this path. If you ran this on a bigger sample, say 100 individuals, let's say 20 of them had this path. You could say, do these 20 individuals that did have this path differ from the 80 that did not in any meaningful metric, right? You can run tests like that. Or of course, the easiest one is run like do individuals in subgroup 1 differ from the individuals in subgroup 2 and whatever outcome you're interested in. But in that way, GIMME gives you a lot of different levels of information that you can use for some downstream hypotheses. And that's what we're going to think about. And one of the cool things about GIMME is you have a lot of different options. People using it in really creative ways are going to think about a couple of the main ways that I've seen or think are especially interesting. We're going to run some test code or how we can think about some of these things. If you go back through this workshop, I linked this website, Tar Heels Live GIMME. It's just the kind of source website for GIMME. On it has a papers link, so you can see what people have done, and also see some of the other written tutorials for GIMME. Okay, so some ideas like, did you find any data-driven subgroups? Were they validated? I linked a place how you can find that. How many group levels did you find? You can kind of quantify how many group level paths, how many individual level paths. You can do different things like that. Let's see. So one of the first things I want to think about doing, so let's try to do this. So let's create a data frame that contains all the non-autoregressive group level paths, their beta weights, and their standard errors for all the participants. Right, so I showed here, sorry, that's where this information is stored. So we want the paths, we want the betas, and we want the SEs for all participants, but we want to kick out the autoregressive paths from our data frame, because let's say we're not interested in this right now. Let's take a second to think about how we could write that code. And if anyone wants to speak up of how we can maybe get started with that, we could run that as well.
Anyone needs a hint? We're kind of looking at like column names almost. Gives anyone kind of a hint towards how you might be able to do that?
Since I forget how our indexing works, I like using these buttons over here where I can see if I want to get, for example, the beta column, I click this, and I say this is the code to access the beta column.
Actually pretty cool. I didn't know that.
No, I also didn't know that.
Yeah, I also didn't know that, and that would have been really helpful to know a long time ago.
Yeah. I forget the indexing with like lists and everything. That's awesome.
Well, that is awesome. Yeah.
So if I ran this, like I would just get, these are all the beta values, right? So yeah, it's cool. So maybe with that hint from Katie, one of the first things you'd want to do is create just a smaller data frame that has the variables of interest. And if we're thinking about this like sequentially, we'd probably want to get that data frame to start and then maybe kick out the autoregressive paths after that once you have it all set up, right? I guess you can only see my R for now. So using that little shortcut we found, if you wanted to access all these column names and put them into an easier data frame, this would be the code, right? So creating a data frame with this data frame command, here we're having, this is actually in the file. So this is the name of each subject. Here we're getting the level, group, subgroup, blah, blah, blah. right-hand side, left-hand side, beta, SC, right? So we're just creating a data frame that's concatenating all these individual columns taken from that list. Now it's set up all nice like this, right? So one of the other things I asked to do was get only looking at the group level paths. So to do that, let's first make the column names nicer. Just by changing them like that. So if you wanted the index where you only have the group level paths, right? So the level columns set if they're group paths, subgroup level, or individual level, we could subset this data frame to only include rows where the level is equal to group, right? So we can run that. And now this was 1208, now it's 720. If we look at level, it's only groups. And the last step we wanted to do, which I'm going to give you a little bit more time to do, is we said the autoregressive paths were the first 15 for each individual. GIMME's nice that it organizes it in the same way for all individuals. Since we have 15 autoregressive paths, so it's the first 15 rows for each individual. Can anyone think of a code where we can kick out the first 15 rows per subject ID? I don't think that will quite work, just because if we're looking at here, they don't have the same name because it'd be right caudate lag and right caudate, I think. It's a good idea though. I'm sure there's a way to do that where you take only maybe the first X characters of the name or ignore the last 3 characters of the name.
All right, I'm sure you have a better solution than this, but I would write a loop and read in each subject number, read in the data for each subject number, and then
The first 15. Yep. That's probably how I would do if I were also coding this, but to make things clean and fancy, not going to know how to code, I wrote it like this. And essentially, this new call rbind is essentially like doing that loop automatically for us, so we don't have to write it out. It's applying the split command. Oops. We're using lapply to apply a command over a list, and that what we're doing is splitting. So we just saw this command earlier. We're splitting the group paths all by the ID, so splitting them by individuals again. As characters just getting their names, and then as we split them, we're taking out the first 15 rows. So this is the exact same thing as doing a loop, like you were saying. This is just a cleaner way of doing it all in one code. Using this fun apply command. Let's see, Tom says, yeah, so I think this would probably work. Let's test it out. Yeah, this is the same thing that we were saying earlier. We couldn't just run this part because they don't have the exact same name as that lag part at the end. So what Tom's trying to do here, I think, is take out this lag part within the subcommand. Let's see how this goes. Not well, Tom, but your fault.
I think it just needs the data frame in front of data frame $lag, and it might or LHS, and it might work like cover. There are many different ways of messing with it.
Yeah. I trust you. There's probably something missing, but I'm confident there's some way to get this to work. Or we can do it through this. Right. So we lost 30 rows here. I was thinking if that makes sense. We had 20 individuals or 300 rows. We lost 300 rows. We had 20 individuals. There were 15 autoregressive paths each. So we lost 300. That adds up. So we probably took out the 15 autoregressive paths for individuals. And now we have this nice data frame. Whereas we have a subject ID, group, our path, it's beta and SC. And this would be a pretty good format. Like if you wanted to do some downstream analyses that tested how individuals defer on specific paths, this data frame would be a good starting point to do any of that. And I have this written out in the code here. Okay. Another task. So we're going to be working from the data frame we just created. So if you haven't run that code, you can copy paste all of this to do that for you. Or want to create a clean table that can maybe put in a manuscript that includes each group level path, its average beta coefficient across individuals, and the average standard error. Because if we were reporting our results from GIMME, we'd probably want to say, here are the group level paths GIMME identified, and here's how much, like, here's the average coefficient, right? That'd probably be good to report in a manuscript. So how can we create a table that does that for us? Oh, I'm not showing my Google Chrome. I had to realize that. If you go to 6.2.1 in the GitHub, that's what I'm talking about. So as a starting point, we'd want create a data frame that's going to be our table. So I'm just going to fill it with NAs for now. We have 21 rows because we have 21 group level paths. Let's see, how did I find that actually? So if you want to find out how many group level paths we have, we can run this. So remember, this group paths is all of the group level paths outside of the autocorrelations. If we divide the number of rows by the number of participants, we get the number of group level paths, right? So that's 21. So if you want to create a data table with those 21 rows, 2 columns just for the beta for the SE. Or for the path and for the beta of the SE. So the way I'm setting up here, we're probably gonna have to use some funny paste commands. Any takers for suggestion to go from here? Maybe first, how we can get the group level paths, assuming they're the same order for all participants as they are. So how can we list these 21 paths out?
And you want the average for all the subjects?
First, let's just get the names in there.
Oh, okay, the path
The
names
names of the
okay.
paths in a single column. So not any of this left-hand side, right-hand side stuff.
So like a paste, some sort of paste commands where you paste in column name 1, column name 2, some sort of.
Exactly. Very good. Right. So our first column is where we want the names. So we're doing paste 0. And we said they're the same order for all participants. So all we need to do is get the first 21 for any participant, or the first 21 rows in general. So I renamed them from to up here. So I'm renaming them the first 21 rows, concatenating this arrow, and concatenating the 2 ROIs. And that ends up looking like this, right? And this is kind of what Holly was suggesting, and is looking pretty clean, where we have a path going from the left insula to the left putamen, and so on. And now, how can we get the beta and SE values a similar way? This one took me some thinking, so we'll see if anyone's quicker than me. So we need to average across individuals, but for the same path.
I feel like you'll have a cleaner solution. I would probably start with a for loop and take the data from each individual spreadsheet and then use the mean of the like new data frame that I created from that. But that's definitely like a little roundabout.
How are you looping? What are you looping over?
The subjects. Because they're in different data frames, right?
You could split them into different data frames, yeah. But right now they're all in this
Oh.
long.
Sorry, I got confused at how the data was.
So we're working from
Oh, this one, yeah.
this essentially.
Okay. So you could just mean of the data frame name, $, beta, right?
Mhm.
Or
But we
average.
need to average. So the first row of the first subject with the first row
Yeah.
of the second subject, and then so on for all 21 rows per person.
Can use the group by left-hand side or the from and to and do the summarize function to get those means.
Yep. So group by, if you're in a tidyverse world, would be the cleanest way to do this. I try to stay out of tidyverse because I don't understand the pipe. Literally, that's the only reason. This thing makes no sense to me. I can't figure out what it's doing. Never makes sense. So I avoid it when I can. So a different way to do this was kind of force our own group by. And that is I created a sequence 1 through 21. And I just put that on the data frame. Onto this. So I have 1 to 21 just repeating. So now I can average all rows that have 1, average all rows that have 2, average all rows that have 3, and so on. So it's essentially just doing split, but in the forced way because I don't understand tidyverse. And now that I've labeled the rows, I just average all of them based on that label. And I'm just doing the same paste by pasting the beta value, then doing some paste of parentheses and getting the standard error. And so now we have the path, the beta, a nice rounded beta standard error, and we can just export this to an Excel and put it into Word. And now we have a nice table to put into our manuscript. Cool. Okay. So those are all group level information. So for a last task for this, how can we create a data frame that lists all the individual level paths, the name of them, and how many individuals had that individual level path? So we want a similar data frame that lists first the name of all the individual level paths, and then just how many individuals have that. This is task 3 if you're on the HTML document. What would be a starting point?
I guess you gotta go back to the initial output table and select only individual paths instead of group paths first.
Yep. That would definitely be first step. Right, so we're back at the original output object. I'm just saying the way I'm doing it here, you could do different ways. The way I'm going to do it is I'm first going to get the indices of any rows where the level is individual level. And then what I'm doing from that is I'm taking the paths. All I want right now is their names. 2 and 4 is 2 columns. So here I'm getting the indices, then I'm putting those indices into here to index based on those. Right. So now here are all the individual level paths. And the way I did this, where I just indexed any paths that were individual level, and then I got a data frame that contained all of them. There are going to be duplicates in here. And those duplicates are what we need to count to figure out how many individuals have those paths. So can anyone take us from there home? Or we can add a third column onto this that just says how many people have this PCC to LNA CC path and remove the rest of the duplicates from the column, from the data frame.
My instinct would be to like just collapse them into one variable, and then there's got to be like a built-in R function for like counts for individual things. I don't know what it is, but I would think there is one.
Yep. Similar to what I'm thinking. Let's see. Really gave me code. Let's try this.
Oh, sorry, yeah, that would only remove all the duplicates, not necessarily count them.
Right. So we need to count
Yeah.
them first.
Yeah. I got
Ron, can you
excited
tell me
when you
yours one more
described
time?
it.
Oh yeah, I just said I would combine the two ROI variables into like the left-hand side and right-hand side variables into one. And then I don't know what function it is, but I'm assuming that R has a built-in function somewhere for like producing counts for each unique item that appears on the list.
Okay. So I cheated and I had to look this up because I couldn't figure it out myself. So I was curious if anyone you could beat me. So the way, and Billy's correct, this would remove the duplicates, but we first need to count how many there are. So this is the tidyverse solution. Let's see if we can figure out together how this is working. So we're creating a new data frame that's piping the one we just created as the name into group by all and counting. So I don't get it. I don't get tidyverse. I don't get it.
It's just it's taking the product of the thing on the left and funneling it into the thing on the right. So it's just like you're starting off with like your data frame, then you're going to go ahead and find like whatever thing you're grouping by, and then those groups you're going to funnel into the count thing, and it should like count the. I mean, I guess it's like kind of like broad overview, but yeah, it's just like input, output. I do find pipes very confusing though. It took me forever to like figure out even basic pipes.
And you don't even need to use the pipes if you just put the data frame where it goes and follow through the operations. It's just moving some of the clutter out of the functions.
Exactly. Yeah,
So this is the same as pretty much.
And yeah, and if you even put that inside count, it would be like that. It's like nested functions almost.
Right. Okay. So let's see if this is the thing. So this gives us, sorry, moving you all around. So it created this n column for us, and it shrunk it to where we only have the unique, or there were 159 unique paths, and we have an n that just says how many of each unique one there were. And just again to highlight, we only had 20 individuals, but we have 159 individual specific paths. So again, a good amount of heterogeneity there. Let's try it the non-tidyverse way. Beautiful. Wow. See that? I can understand. Okay. And so with the individual specific paths, you can see most of these are just one, which is not shocking. So we only had 20 individuals, right? But let's say we had 100 individuals. If we had 100, if does one person having a path mean that much? Probably not, right? So let's say you want to subset these based on paths, at least 3 or 4 individuals had it, right? And it seems like you will have confidence subsetting, so I'm not going to test you on this, but let's just say greater than 3, so at least had 4 paths, or at least 4 people had that path. We only have 2 individual specific paths where 4 people had this. So 4 is still 20% of the sample. So again, 20% of the sample had these 2 paths. So that seems somewhat relevant, right? That seems somewhat meaningful, 20% having them. And you can think about what that means for whatever conceptual work you were doing. Cool. All right. So these 3 tasks were all on the HTML document, and I think are useful for starting to work with some of the group and individual level information, which if you use GIMME, probably the main point you're thinking about. Let's also look at some of the subgroup level stuff. So the first question, how many individuals are in each subgroup? So let's go back to R. So the first question we're asking is how many individuals are in each subgroup? Where could we start to think about finding that information? Or if any of you have this open on yourself, can you find it and point it out to me? Briefly mentioned it earlier.
Well, if I were doing this at this point, I would scroll back up in my code and copy and paste whatever I did earlier, but I do not memorize my R syntax.
Great. So what we saw earlier is we're in, again, pretty much all of our relevant info is going to be this path SCS sublist. The last thing, we have sub membership, right? But the only trick is this is duplicated long ways. So for each person is duplicated for every single one of their paths. So how can we go from this information to a simple data frame that just shows each individual and their subgroup membership, or counts how many individuals are in each subgroup?
So we could wind up subsetting out each unique observation from that group, and then like reading out that that results in like a summary or table or something like that.
That's exactly how I would do it. And you all are looking at my R now, correct?
Yes, we can see it.
Cool. Right. So just as Billy was saying, you want to remove the uniques or remove the duplicates. So we're getting rid of the duplicates. What that is it looking like is here, right? So only have one row per individual because you remove duplicate file, or that's ID name essentially. And now we have this data frame, and essentially we need to count the sum membership, right? So we could just do a table of sum membership, and we say you have 11 people in subgroup 1 and 9 people in subgroup 2. That would probably be relevant information you'd want to produce in the main script as well. Okay. And for the second thing for subgroups, second task. So earlier when we looked at them visually, we saw that one subgroup had a lot more paths than the other. Let's try to quantify that. How can we identify how many subgroup paths are in each subgroup? And remember, for one key thing with this is a hint, is that all individuals within the same subgroup will have same subgroup level paths. So within the same subgroup, they are identical. The presence, at least, is identical.
So then can we just subset the paths for a given participant and then count by the like level variable? But specifically for the like subgroup, or subgroup value.
Yeah, exactly. So if we look in our object, we can see, let's say we just paste this for a second. We can see conveniently that subject 1 is in subgroup 2. Subject 1 is in subgroup 2, and subject 2 is in subgroup 1. And since the paths are going to be the same across the subgroups, we can use that information. Right? So subject 1 is in subgroup 2. So we can take this. So subgroup 1, let's do it like this. Okay, so we're taking just paths for only subject 2. And we're saying we're doing that because subject 2 is in subgroup 1. Okay, so now we have all the paths for subject 2. And as you all can probably take it from here, all we need to do is then subset this again for only the paths where the level is subgroup. And if we just wanted to count those, we could just, if we just wanted to count those, we could just do n row of the rows that have this level, right? You would get 19. Or 9, I guess. Okay. And we just do that again for the subgroup. Okay. So the last task, and this one's going to be both what I think is the most interesting, but also the most complicated. So let's make sure we can all read this together. So I think this is going to go back first to thinking about the differences between effective connectivity versus functional connectivity, right? So right at the beginning of this workshop, we talked about how functional connectivity is very independent, right? We correlate X and Y, X and Z, Y and Z, and those are all considered independently from each other. And that's different from what we're doing here, where this network is all interrelated. We have X can go to Y, which goes to Z. That's essentially an interaction, right? Because these are all just SEM models. So what I want to do, and I think is becoming like more interesting with these GIMME models and just leveraging the kind of information it gives us, is I want to treat the information as less independent and more like multivariate, dependent on each other, because that's how it's being estimated, right? So yes, we could just test, does the pathway from X to Y predict question outcomes? Sure. We could test that, or we could try to think about using multiple paths together in the same test. And one way of doing that is creating a hub, which is essentially a node or set of nodes. And this gets into network theory. And you can think about how important of a role that hub plays in the overall network. So the hub could be one node, for example, like the ACC, the anterior cingulate cortex. And then you could ask, how many connections does this node or hub have across all individuals? And does how connected this node is affect any external outcomes, right? And so you can think about it in just the number of connections. That'd be kind of just a degree where you could weight that. So multiply the connection existence or not by its beta coefficient, and you're getting a strength of that connection. And if you add all those together, you're kind of getting a centrality. And the centrality is essentially just asking how much of an influence does a certain node play in the overall network. If that centrality is really small, it means there's pretty little connections that are pretty weak with other nodes, so that this hub is unimportant. Or if you have really big centrality, you would be saying this hub is really important, has a lot of different relationships with other nodes, is creating a big influence in the overarching network. So let's think about how we could calculate a centrality value for a hub. And here we're going to need to use our grep skills, our text skills as a hit. So let's think about a dorsal striatum hub. So let's say the dorsal striatum consists of the caudate or putamen, and we want the left or the right. And we wanted the weighted degree. So we need to see, does the path exist? And we need to get that beta value out of it. And we want to do an absolute value of those beta values so we can account for the positive or negative influence, right? And we want to sum. So essentially what we're doing is summing all the paths together that contain either the caudate or putamen left or right. This one probably will take a little bit longer, so let's give a few minutes for people to start thinking about how they can start to tackle this one. Unless you all are just way better coding than me. So it took me a while at least.
Definitely don't think we are. You've had some really good R nuggets today.
Well, I've had time to set this up at least.
I am interested because you mentioned how you're thinking of it in kind of like a weighted thing. This is different than what I think you were thinking of, but could you also create a separate variable in which you like give weight to only paths that include the dorsal striatum, and then just you could do the math from there, like 0 or 1, basically, like actually weighting them? Or would that be more complicated than what you were thinking?
I think the way I actually said it, maybe it made it more confusing than it needs to be. You probably don't need to test first the presence or absence, because if it's absent, it's just not going to be included in the data frame in general. So really all you need to do is just like, if it's there, get its beta value. So like if the path includes one of those regions, include its beta value in a summation. Trying to get my R back in share. There we go. that should make the formatting easier to start. This is at least how I started it. And this kind of goes back to what we did earlier. So first, just getting a data frame that has the relevant variables. So we have file, just subject ID, level, right-hand side, left-hand side, data, SE. And making easy column names to work with. And the reason I'm redoing this is because earlier, if you remember, we changed this data frame where it only included group level paths. But here we don't want to do that, right? We want to also include subgroup and individual level paths. So I'm skipping that step we did earlier, where I subset it based on group level, but I am removing the autoaggressive paths. So that gives me ultimately to work with a data frame that has all of the paths of any level for all subjects and the relevant variables in the nice, easy to read format. So that's where I'm starting. If someone thinks of a way to move forward, call it out. Another formatting thing that Rana pointed out earlier is it might be helpful to create a single path name variable that doesn't have to, so you don't have to deal with like from to kind of thing. In this code, do that. All right, so now I have a path variable which includes both regions in the same name. That can be helpful.
So looking at old code, this is where I would go over to the tidyverse and use div layer, select, and then like, oh wait, no, this would be for column names. Backing out.
I think sounds like you're thinking similar to how Tom's thinking. So see, Tom is subsetting. But Tom, I think wouldn't you also need these same things, but two? It's like the same options, but replace from with two.
If it's part of the selection that the I wasn't clear if you were meaning only from the
Right. Yeah.
or if it was both.
Yeah, I guess it could be either way. We'll keep it your way. That makes sense.
Doesn't matter. I mean, it would just be the copy and paste job of putting in the from or the to.
Like this, and we try to figure out just a summation. And then I'm trying to figure out the looping piping here. Tom, what is DSTR?
That's just what the new variable would be called.
Oh, okay. And that looks like pretty clean and efficient. Are there other ideas? Because I have it one other way. Or do you want me to hold off while people think? So I was kind of pointing out earlier that you can think of different ways if you only want to include paths starting at one of these regions, or if you want to include any path involving them whatsoever. I was doing it that latter way. Probably should think a little bit harder about this, but if I want to do it that way, I would include any of these paths. I'd also want to think about their lagged forms. So I'm creating a string that contains those. And a much more laborious way than what Tom was doing, but let's see. So I first for the fellow loop fanatics, what I wanted to do here is just use grep to ask, does, so I have this variable name path clean path, I have that here. That's essentially asking, does this value, that variable, contain any of the strings in this variable just created, which are these. So do any of these paths exist in this? If so, I'm going to create a new column and just mark it as a 1. And that way I can kind of index of variables or index of paths that include any of these names that I can then add over. Or not. One wrong here.
Sorry, in the paste command that you have, what's the backslash greater than or less than symbol?
This part, yeah. So I'm looking forward. I think there's one of the COG workshops to like text searching or text kind of stuff, because I don't really understand either. I had to find this online, but I think pretty sure what this is doing is asking, it can be any of the things in here.
Okay. All right.
I
Cool.
think
All
that's
right,
what I gathered.
I thought it was like a quoted text that I wasn't getting. Okay.
Yeah. No, it's like one of the weird like regex functions, I think, however you pronounce that.
Okay.
Yeah, I'm excited for the COG full advertisement for that, I guess. There's a text workshop. Why did this not work then? Oh, now it did. I guess it's not something going. Okay, so now that ran, I now have added just zeros and ones, 1 being if it has any of my regions. Which looks like it did not work right. Why did it not? Because these should probably be 1s since these have the putamen, right? Well, never mind. Okay, well, this code doesn't work. So Tom wins. There we go. Any other ideas?
I have one other one that I'm working on just to clean up some of that, but yeah, and you're looking in the right spot, so you end up having those lags in there. So
Figure why this didn't work. I must mean the workshop with this, because why would this not work?
I mean, I'm not really sure. I'm not really familiar with the grep function, or what the function of the carrots are with grep there. I mean, it could be, is it possible that this was like grep from like a Python workshop or something like that?
I think this is a,
Was it definitely R?
yeah.
Mhm.
So what I'm trying to do is, does this exist? So I think I must have an error in one of these iterations. That's the issue, I think.
Mm.
Anyone else come up with good ideas? Oh, no, because I have the names wrong. That's probably why. Oops. Right. Yeah. Try this again. Okay, so I just had the names written out wrong. I had the left to right after, it should have been before. Now it does work. So again, what I'm doing is I'm searching, does any of the striatum elements, so any of these match any, or does the row in the path, does the path that the row we're looking at match any of these striatal variables? If so, give it a 1. And that's what we did successfully do here. And now I have it set up where it's pretty easy. You just add based on if this is a 1 or not, right? Subsetting that. So finish it off for posterity. And if we change, so this, just doing a simple loop, adding together if the striatum equals 1. And we should have nice variable. This, for each subject, now has a hub strength value. And these are a lot bigger than what Tom got because we included paths from or to in the lag variables as well. So you can think about doing it different ways, depending on your question. And that was the last task.
Right, great. Do you is there any other sort of like closing things that you wanted to touch on, or
Probably the last thing to say is that if people want to use GIMME, which I highly recommend, I think it's a really cool tool. I think it's a good starting point. Places they should definitely go to get more into it is, like, first, I'm happy to help with anything. But the GIMME website here has really useful tools, they have different tutorials, all of the papers people should look at. And I also put the 2 really key papers here as a link. People should definitely use those resources because Dr. Katie Gates and her group have been really good at creating these open and usable resources.
all right,
That's it.
awesome. All right, well, thank you very much, Matt, for throwing together like a really great like quality tutorial. We're really happy to like have it on the website, especially as like the first iteration of like our experiment with like trying to get folks to like do presentations, something that they're passionate about. Thank you all for coming too. Katie and I are really happy to organize all this stuff and have you guys come here and learn this from us. I think next week we're going to have Helen Schmidt from my lab do machine learning tutorials in R using the RPart package. I think she has like k-means clustering, decision trees, PCA. There's a few other things. So it's I think it'll be really good next week as well. But I think that's it. Again, thanks, Matt. Thanks everybody for coming, and we'll hopefully see you next week.
This was great, Matt. Thank you.
Thank you all.
Great, thank you.
Thanks.